What is a Markov category? Markov categories are a way of doing probability theory from a dynamical or process-oriented point of view. The idea is that the main structures that we want to study are transitions with randomness. And that's why category theory is heavily used, because it's all about arrows and composing arrows. It's a theory of processes in some way. So before we get to the main definition, let's look at some main examples. The simple example is Finstock, which is the category of stochastic matrices. What does this look like? Imagine two sets, and you see from each point of A, we can transition to points of the set X with different probabilities and have this for each point. This construction is known as a stochastic matrix, which you can see as a matrix having all the elements taking values between 0 and 1, and where all the rows sum to 1, or all the columns is here, depending on your convention. Okay? The entry in your matrix can be seen as the conditional probability, in this case, of going from B to Z. Now, these form a category, meaning that you can compose them as long as the dimensionalities or that the domain and codomain match, right? So if you have a new set Y or K, then you see that what's the probability of going from A to K? Well, you have to first transition, say, from A to X, and then independently from X to K. You have to multiply these and sum over all intermediate states. So here's the formula. And this formula is known as the Chapman-Kolmogorov formula, is, for example, how you compose transitions in a Markov process. Now, the important part here is that the transition from first part and the second part are independent. So the basic building blocks here have independent transitions, but of course, as we will see, you can encode more general interactions in if you refine your structure a little bit. Okay. Now you see also that, say, the blue arrows are just a probability measure on X, right? So morphisms or matrices from the one-point space are the same thing as probability measures, which we call states, as in random states. Okay. In this case, they are probability measures of finite support, and we see more in general, they will encode simply states. Conversely, you can view a stochastic matrix or a morphism as a family of states parameterized by A. You see, in this case, there's two probability measures on X, the orange one and the blue one, indexed by the points of A. So you can go from states to morphisms, or from morphisms to states, depending on your point of view. This is our most basic example. Let's look for a slightly more general example and move from discrete probability to continuous. So now you see, we can't really say, let's go from a point of X to a point of Y, because that in general might happen with probability 0. So what we have to take is events of Y, or measurable subsets of Y, and look at transition from points of X to measurable subsets of Y. So this category now, as objects instead of sets, has measurable spaces, so spaces with a sigma algebra of events. And the morphisms are what's called Markov kernels or stochastic kernels, which are the continuous analog of stochastic matrices. So these are maxims that take a point of X and a set of Y, so a subset of Y, an event of Y, and give the probability of ending up in A if we start in X. Okay, so for each X, this is a probability measure on Y. Again, if you want, it's a family of probability measure of Y indexed by X, but moreover, it's indexed measurably in X. Okay. Why do we want this technical condition of measurability? Well, because we want to integrate over these objects when we compose them. So just like before, if we want to compose two of these objects, we have to sum over all intermediate states, but now the sum becomes an integral. So the interpretation is exactly like before, except that now this makes sense only if, for example, H is measurable in Y. Otherwise, the integral is not defined, and that's why we require measurability. So this formula is, again, the Chapman-Kolmogorov formula in continuous space And it's just like the previous one, except the sum is replaced by an integral. Okay. Now, given every measurable function, so without any randomness, we can always define a kernel that does the following. It gives probability 1 if it's mapped exactly. So if the point where we map our x is in our A and 0 otherwise. This is like a 0-1 Markov kernel, or like a deterministic Markov kernel if you want. So defined just by a function. There's no randomness involved here. Okay, so for every event A, we are sure whether f of x isn't there or not. This defines a functor from mass to stock, meaning that the objects here are the same, just measurable spaces. Measurable functions, the morphism of mass, are mapped to these particular kernels. And this assignment preserves identities and composition. Okay. All right. Let's now go towards the general definition. We need one more additional piece of structure, which is monoidal products. So you probably know that probability is not just about measure theory and measurable spaces, but it's also and mostly about interaction of different random variables and correlations and so on, right? So we need a notion of interactions and of composite states. Given to objects x and y, we need the notion of their product. So imagine something like the Cartesian product of sets or of measurable spaces. Okay. And moreover, if these objects evolve, so if we have some transition, possibly random, from x to a, from y to b, then we get separately transitions here. So it's not just a product on the objects, but it's also a product on the morphisms. So just like a product is a binary function, here we have a binary functor, as in a functor of two variables, jointly functorial. It's called a monoidal product, and whenever it satisfies the right notions of associativity, unitality, in this case up to isomorphism, we call it a monoidal category. Okay, so I don't want to go into the details of what monoidal categories are. You can look them up, but interpretation is you form products of spaces and of arrows independently. And moreover, here you want a symmetric monoidal category, so you want to say that x times y is kind of the same as y times x up to isomorphism. So what you can have here is called a symmetric monoidal category, okay? But more concretely, what does this look like, say, for Markov kernels? So the composite or the product kernel here on this product of measurable sets, says S is a measurable subset of A and T of B, then it's just a product of the two, right? Of course, so this is not the most general measurable subset of A times B, but you can extend it to A times B in this case. So in particular, if there's no dependence on x and y, so if these are states, then this is just saying that the product kernel, this probability is the product of the two probabilities. So it's kind of telling you that the sets S and T are, as events, independent. Okay, so you're combining these two things, forming independent transitions. In monoidal categories, it's helpful to use string diagrams, so to write these things as these boxes. So the idea is objects are wires. Imagine something like states of potential in electrical circuits. And morphisms are a little bit like the electrical components. So here we read them from bottom to top, okay, a little bit like in physics. So the morphism F here is a box going from X to A. Imagine a bit like a resistor in electrical circuits, if you want. And Y goes from G goes from Y to B. And if you put them next to one another, it's a little bit like composing them in parallel. Like this is the joint transition given by just applying F and G independently. And you see here a more general thing from XY to AB will look like this H on the right. But you see this H on the right kind of symbolizes that there could be some signaling here. So it could be that A depends on X and Y, same for B. However, here instead, in this product of these two are independent, as in Y has no effect on A, okay? So this is more or less the interpretation of these string diagrams. Now, we need one more thing. Remember that we wanted a special something like 1-point space, such that morphisms out of it are states of X, or like probability measures. And so we need a special object called the monoidal unit, here denoted by I. So in general, I is not the unit interval. I is more like a 1-point space for us. And morphisms from the monoidal unit, we write them as these triangles. The monoidal unit is represented by like nothing. It's kind of like neutral element of this product. So you don't write it really. And so morphisms like this are written by triangles. So a triangle here is something like a random state. So in stock, this is just a probability measure, so a cardinal with no input. In Finstock, it's a discrete probability measure, so a stochastic matrix, which is just a column. Okay. All right. So what is a Markov category? Markov category is a symmetric monoidal category, where now each object is equipped with these two special maps with, so to say, copy your state and discard your state. So we write these maps in state diagrams like this. X is copied into these two things, and X is deleted. Now, for those of you that know about quantum probability, you might think, okay, this can't be natural in quantum physics. I'm not saying these maps are natural. Huh? So far, everything is quantum compatible, but we'll tell a little bit more about that in a moment. So these copy and delete maps need to satisfy these compatibility diagrams, which kind of tells us that copy and discard is indeed a good interpretation for this map. So here we have to say that these copy and delete maps satisfy a commutative comonoid axioms for each X, which means what? Okay, so the first of these equation tells us that, you see, if you copy the state of X and copy the first copy, it's the same thing as copying the second copy. So you just have 3 copies which are equal. This condition tells us if you copy X and discard one of the 2 copies, it's the same as doing nothing. And this one says that if you copy and switch the 2 copies, then it looks exactly the same. So that the 2 copies are the same, really. So this all tells us that this interpretation of these maps is indeed compatible with thinking of copying stuff, right? We're not, I don't know, decomposing X into 2 components, for example. Because if that was the case, then you see associativity would not quite be holding, at least not in this way. And there are more conditions here. So we want the technical condition, which tells us that copying is compatible with monoidal structure. And more interestingly, we also want this condition, so that for every morphism F, applying F, so applying something to our information and discarding it, discarding the result, is the same as discarding the information in the first place, right? So you see, not using this information, it's like there's only one way of not using your information. So the people familiar with quantum formalism might recognize this as a notion of a unitarity of our things, and that's indeed the case. So this has to do with the fact that probabilities are normalized. Okay, you can check that for example, stochastic matrices. This corresponds to the condition that the sum of columns of our matrices is 1. You might want to relax this condition and not require this axiom. If you want to do, as opposed to probability theory, more general measure theory, or if you want to do unnormalized things. So if you do that, so you discard this axiom, then you have what's called a CD structure, like copy discard structure, or GS, like a garbage share monoidal structure. And those are close relatives of Markov categories and much older concepts. So sometimes in categorical probability, you use those structures, but for us in this talk, we will talk about Markov categories in this form, so we will require this axiom, okay? But again, there are more general things without these axioms, which are much older and date back to the 90s. All right. What are these copy and discard maps in our examples? The copy maps mostly. So in Finstock, okay, you see X times X is just the Cartesian product. And if you have the 2 elements, you have 4 possibilities. And what are these copy maps? Well, okay, X, you want to map it to, I want to say this diagonal embedding. X goes to X. X, you copy this value. It could have been Y, but these 2 things need to be equal. And same for Y. All right. So of course, this is a function, not a kernel, but as a kernel, as a matrix, you see you map X with probability 1 to XX and Y probability 1 to YY. Everything else has probability 0. These things have probability 0 of being different because these are not copies. Okay. In stock, well, that's again a diagonal map, but now in continuous versions, you see something like a diagonal embedding of the unit interval into the diagonal here. So again, this is a function, not a kernel. What's the kernel? Okay, so take a measurable subset of A, which specified this like the vertical position, and measurable subset B that specify the horizontal position. Now, when is XX in B in A times B? Well, if X is in A and X itself is in B, so if X is in this intersection of the two. And so the kernel is this, at least on product sets. It's 1 if X is in this intersection, 0 if X is not. And so in particular, it's 0 if A and B don't intersect. Okay. Now, of course, you have to extend this to the whole sigma algebra on the product, but in this case, you can. Right. And you see that the copy map then is related to the intersection of measurable sets. You'll see more on this in the subsequent slides. Right. Now, algebraically, we can interpret Markov categories in terms of monoid structures in the following way. So you probably know from either quantum probability, like sister algebras, or from algebraic geometry, that if you take the category of some spaces of some kind and reverse all the arrows, then that's a little bit like category of functions over your spaces with values in C, in R, or things like that. Okay, that's the core of the Gelfand-Naimark theorem, for example, or like sometimes the Nullstellensatz have these interpretations and so on. So what does an opposite category to a Markov category look like? So now you see the map, the copy maps become a little bit like multiplication maps, and the discard maps become a little bit like unit elements. So if you look at function on X and you replace X by the functions on X, then the copy maps is a little bit like the product of the functions, the pointwise product of functions. And I is just a function that's identically 1. All your axioms, so for example, this axiom here, the one that's copying twice is the same as getting 3 copies. This is associativity of this product. And the other condition gives you unitality and the symmetry of the product. So basically tell you that the functions of your space form commutative monoids. So for example, rings with their multiplicative structure. Okay. So Markov category is a little bit like the opposite of category with a function over a space. However, remember this axiom. So this kind of tells us that f of 1 is equal to 1. So this tells us that, for example, commutative rings and unital maps up is a Markov category. The unitality condition is from enforcing this axiom, this yellow axiom here. Okay. There is a quantum version of Markov categories defined by Arthur Parzignat, and it's not defined by relaxing the symmetry in the symmetric monoidal category, so in the tensor product of spaces, but rather remember that copy can be like the copies can be switched, and that's the same result. That's the part that is relaxed in quantum Markov categories. So you make these structures not quite commutative monoids or commutative comonoids, but rather just monoids and comonoids with an additional grading. Okay, you can look in the reference for more on that. Okay, but so algebraically, the opposite of a Markov categories is like spaces with function on it and maps between them that preserve the units. So again, you see this is a kind of a normalization condition, right? The integral of 1 is 1, so it's like probably the measure of integration is normalized. Okay, the total integral is 1. All right, now let's start with the most important piece of structure in our Markov category. So we say probability is all about looking at products of spaces and their interactions and correlations. Let's do that. So suppose you have 2 marginals on these 2 like unit interval spaces, so P and Q, and you can form their product, right? which is like considering these two probabilities independent. I colored one in orange so that you see these all have the same structure. So this is the product. And as we saw, as string diagrams, you write this by just forming the tensor product. So just exposing these two. So this joint state R is the product of these two marginals. Now, more in general, you see this joint here, if you project it, it gives again our marginals, but it's not the product of the two. You see, these are not independent now anymore. So how do you say when some joint is still a joint for these two marginals, even if when it's not their product? Well, if you discard y, then you get x. That's like summing over all the y's or integrating over them in the continuous case. Okay, so this equation here for the discrete case and a similar one for the continuous case can be represented by this diagram here. This dot is discarding y, so unobserving y, integrating over y. So this is the way of saying that P is the marginal of R on X, which is obtained by discarding y. Okay. Of course, the same thing by discarding y and obtaining the marginal over y, discarding x. All right. So the product is, of course, if you here see if you discard y, you just get x. So it's a special case. So you can prove that if P is a product, then is exactly the product of its marginals, of nothing else. It's pretty easy to prove. So we can talk about independence of random variables in generic Markov categories. So this joint P exhibits independence of x and y if and only if, in some sense, you can split this triangle into the two marginals, okay? So into any two marginals, but then they have to be, of course, its marginals. So this equation is a little bit like this formula here. Okay, so again, it's kind of a graphical model. It's like a graphical interpretation of the independence of these two random variables. More generally, we can talk about stochastic conditional independence. So if this kernel given A makes x and y independent, then that's the same thing as saying that this is the same as copying A and then applying the two marginals. In numbers for Finstock, like for the finite case, that's exactly as this formula here. But again, of course, our diagrams hold more in general for in particular in continuous case. But you see here, why are we copying A? Well, because A here, the value of A in this equation is used twice. So this is not A and A prime. This is the same A. So if A is the same, then these two things are independent. Now, some people might not know why do we want A to be the same, and what's the difference between conditional independence and just independence. So let's give a toy example. Suppose that you sample from some poll that you take on people and you ask these people how often they eat pizza and how often they drink espresso coffee. You might notice a correlation in your data. And you're like, okay, so definitely this join is not the product of the two marginals. These two things are clearly not independent, right? However, suppose you discover that half of the people you've asked are from Italy. And in Italy, people tend to, drink more espresso and eat more pizza, but it's not like it's more likely that you have pizza if you have espresso in Italy, right? People like them more independently of the two. And maybe the other half of your people are from the rest of the world, where again, there's no particular correlation between pizza and espresso. However, this happens, both things happen with less frequency than in Italy. Now, your global data, you see now, in general, marginally, you see a dependence between these two. But now, if these people live in the same country, so if A is the same, given A, that has some variability given by Q, right? A is not uniform. There's Italy and somewhere else. But if A is fixed, if you copy the same A, then K and H are independent. Okay, so this joint might be explained the way, so that the correlation here might be explained by just different origins. if you fix A, then these two events are independent. Okay. So I hope it's clear what you mean then. Same A and why you need to copy A to use the same A here. Now, of course, these data are not real world data. They're not realistic. So I suppose pizza is more popular than espresso. So probably the real data are a lot more skewed to the right. But I hope it's clear why conditional independence involves the copy map. Okay. Given the same country, then the two things are independent. All right. Here is another very important piece of structure for Markov categories. We said that our morphisms are random in general, right? Have some stochasticness, some variability to them. When can we say that they don't? When are they not that random? All right, so we call a morphism deterministic if this equation holds, which means that if applying F and copying the result is the same thing as copying the input of F and then applying F twice, so applying F to each copy. One of my favorite quotes is a quote by Einstein that says that madness is doing the same thing twice and expecting different results. It's probably something that related to quantum mechanics and so on. No, I don't know if that's a madness, but I think that's the perfect definition of randomness. Randomness is doing the same thing twice and expecting different results. You know, that means that what you did involved some randomness, some chance. Say that F is this function. So it takes natural numbers, or like int if you are in computer science, and it flips a coin. If it's heads, it adds 2 to your number. And if it's tails, it adds 3 to your number. So this is a random function, okay? Now let's look at what happens if we start with value of 2. So if x is 2, like you know it's 2 with probability 1, then apply F. Well, you flip a coin, and 1/2 of the times you might get 4, because you have to, get heads and add 2. And the other half of the times you get 5, because you get tails and have to add 3. Okay? And now you copy this result. So you see, you either get 4, 4, because with probability 1/2 you get this and then you copy, or you get 5, 5. You cannot get mixed results, right? Because all the randomness is here, and then you copy whatever you have. So you are sure that whatever you get, the two outcomes are going to be equal. You don't know which ones, right? But they're equal. Okay, so if you're familiar with quantum probability, this is a little bit like entanglement, but this is fully classical. Huh? There's no quantum stuff here. So 4, 4 or 5, 5, you don't know which one, but they're going to be, the two copies are going to be equal with probability 1. Perfect correlation, if you want. Instead, here, if you start with 2 in the second case, you copy these 2, so you have 2 equal copies, and apply F to both copies. You see that, these two coins now don't know about one another. Again, it's not, entanglement or anything. So you might get all 4 possibilities, right? Because these two coins are independent. So here you get independence in some sense. So you see these two states of y times y that you get are fully different. The first one is perfectly correlated. The second one is perfectly independent, or at least perfectly independent given x, okay, given the inputs. Again, you see, if you try these things on different inputs, then you see that they're going to be not that far from one another, right? But if they have the same inputs, then you see the second thing is going to be fully independent, once again, given the same inputs, right? So there's some conditional independence here that we don't have up here. All right. Why? Well, because we flipped a coin. If there was no randomness here, then we wouldn't have this problem. You just have 2 perfect copies of F applied to X. So I want to argue that the randomness here is exactly what makes these two things different, right? Now, for states, so if there are no inputs, then the diagram reduces to this. And What does this tell us, for example, for ordinary probabilities, so for the category stock? So in stock, this is saying us that, you remember the copy map is tested on intersection. So that's telling us that intersection of A and B has as probability the product of the two probabilities. So the events A and B are independent. And you might know these, the probability measures that make all events independent are exactly the 0-1 measures, the 0-1 laws. So if you see, you take A equal to B, here you get this equation, and the two solutions are P of A is either 0 or 1. So these are those probability measures that, given each event, they know almost certainly if it's going to happen or not. No 1/2, no 1/3. So every event will either almost surely happen or almost surely not happen. So these things are not that random, if you want, right? In the case of Finstock, that's the same. That's the stochastic matrices that have just zeros and one. So if they're square, those are the permutation matrices. Okay, so in general, not all 0-1 morphisms are just measurable functions. There are more things like ergodic measures and so on. But if your sigma algebras are nice enough, like fine enough, then these are exactly your functions. So if you take the category Borel stock, which is the subcategory where the objects are standard Borel spaces, like a sigma algebras over Borel sigma algebras of Polish spaces. So these are the spaces where you usually do probability theory in practice, like finite spaces, countable spaces, real line, Rn, which is actually isomorphic to Rn as measurable space, the unit interval. So all these are isomorphic as measurable spaces. So all these spaces are standard Borel, and in there, the deterministic morphisms are exactly the measurable function. So the one coming from this functor K, remember. More general, you get, like if you allow more general measurable spaces, then you get very coarse sigma algebras and you get like ergodic states and so on. So it's also interesting to see when this is not the case. I have a work with Sean Moss about this, but for the purpose of this talk, we can restrict to standard Borel spaces where you do the usual probability theory, and their deterministic morphisms are basically just the functions, the measurable functions. Okay, so this recovers the usual notion of deterministic Markov kernel on the examples of interest. Algebraically, so remember that the commutative rings and unital maps op is a Markov category, right? And more general, you can look at the opposite of Markov categories as something like algebra. So what are states? States are just functions, like scalar functions on your states, like in the case of commutative ring into Z, but of course, more general, you can take R, C, and so on. So what does it mean deterministic? So we say that all morphisms have to be unital for your monoid or ring structure. Well, you see, deterministic, then this means, read these diagrams upside down, that multiplying and applying F is the same thing as applying F in both components and multiplying. So that's the multiplicative maps. So these are unital and multiplicative. So those are exactly the monoid homomorphisms or the ring homomorphism if they're linear. So you see, those are the states which are, in some sense, like applying your function at a point, like a pointwise evaluation of functions. So those are like the points of X as opposed to measures on X. You see, a point application of a function preserves products, right? F of G at X is the same thing as F of X G at X. And that's not the case for, instead, let me say, evaluating the function at a measure, by which I mean integrating it. You see, the product of integrals is usually not the integral of products. But if you're integrating against the Dirac delta, then it is, because you're just doing pointwise application, okay? So the product of functions is pointwise, and that's kind of why deterministic states are a bit like points. So you probably know that, say, for the Gelfand-Neumark theorem, you want ring homomorphisms there. Like sister algebra homomorphisms. And you also see that in order to take the product of functions, then you have to use X twice. See, X, it's not X and X prime is the same X. So once again, you're using X twice, or you're copying the value of X. And that's why the copy map here comes in the definition of product, or if you want, in the definition of deterministic morphism, right? So the product is dual to copying, and you see here you take the product, that's the same thing as in the right copying X. These two things are opposite categories to one another. So yeah, determinism also makes sense in terms of copying, also from the point of view of algebra. Okay, so in algebraic geometry, you want continuous functions to be your morphisms, and so those are ring homomorphisms because they multiply things, right? All right. In a Markov category, the following things are equivalent. First, every morphism is deterministic, so there is no randomness. Second things, the copy maps are a natural transformation. Think of something like a classical version of no cloning theorem here. So we're saying cloning theorem in some sense. And 3, C is Cartesian monoidal, by which I mean that the monoidal product is exactly the categorical product. I mean, some people call it the Cartesian product, but so the Cartesian product of, say, measurable spaces is the Cartesian product in the category of measurable spaces and measurable maps, not Markov kernels. So let's say categorical product as opposed to Cartesian to avoid confusion, okay? So how do you interpret this proposition? So I want to say, so a slogan that I like, which is not rigorous, but I think gives a good idea, is that Markov categories are exactly the Cartesian monoidal categories when you turn on some randomness, okay? This is not rigorous, of course. What's the rigorous version of this? Well, the rigorous version, which is this proposition, is that Cartesian monoidal categories are exactly those Markov categories where you enforce determinism, okay? That's what this proposition is. So that's a way of seeing what Markov categories are. Now you may wonder, okay, wait, what is wrong with the categorical products? Like, why is that not accounting for randomness? Because it satisfies a universal property which is too strong for our purposes. Let me show you an example. So what is the categorical product? X times Y in category theory is such that, it has these projections, but it's such that given map from A to X and A to Y, then there is a unique map into X times Y, making this diagonal commute. Or if you want, given a state of X, possibly parameterized, but let's say for states, given a state of X and a state of Y, then there exists a unique joint state that projects down to them. And that's not the case if you have randomness. Look, you see, this is a possible joint for these two probability measures. You see, that's a map into X times Y that projects down to these two, but this one is too, and these two are different. That's also a joint for these two. So this universal property does not hold. The uniqueness of this dashed map fails. Right? So stochastic interaction, so the fact that there's different ways to correlate these two things, is an intrinsic feature to randomness. So you saw we interpreted determinism as the fact that there could be correlation and independence, and here conversely, we're saying that there are correlations exactly if there's no randomness, right? They're kind of, how can I say, you can interpret one in terms of the other. Randomness is when you have correlations, but also you have correlations if you have randomness, okay? So if you know information theory, for example, that's like a, mutual information is bounded by entropy, but at the same time, entropy is the same thing as like a mutual information with yourself. So correlations and randomness are like kind of two sides of the same coin. And this is captured perfectly by the fact that Markov categories generalize Cartesian monoidal categories. All right. Here is another very practical structure of Markov categories, which is the notion of conditionals. So given some joint distribution, joint state, then a conditional distribution of P given X, if it exists, isomorphism from X to Y. So you see a kernel or stochastic map or conditional probability from X to Y, such that this equation holds, which means what? Well, the joint can be obtained by forming the marginal on X, then applying the conditional given X, and keeping the value of X. So you see, that's exactly this equation down here in the discrete case. P of X and Y, you form the marginal X, you multiply it by the conditional, but then you keep a copy of X. So you don't sum over X here. You don't integrate it over. Because if you did, you just get P of Y, right? So the fact that you're copying X is the fact that here X appears twice in the equation. And then it remains an observed variable. It's not integrated over. Okay. The conditionals do not always exist. So for generic stochastic kernels, so for generic measurable space, they do not exist in general, but they exist in all the discrete cases. And more importantly, they exist in Borel stock. So remember this category of standard Borel spaces. Okay. And that's why this is usually the category chosen to do classical probability theory, between quotes here, because I don't mean classical as opposed to not quantum. I mean not quantum, but I mean traditional, as in not categorical probability. So that's usually done in standard Borel spaces, and the main reason is because they're all the conditionals that you want exist. Okay. What's the most important conditional? That's Bayesian inverse. So you can do conditioning for all joints if it exists, and you can do it in particular for this joint obtained by forming P of X and P of X given Y. So what does the Bayesian inverse do? Conditions, and so it flips this map around. It's a little bit like an inverse. It's called a Bayesian inverse. And you see this diagram then becomes this equation here, which is exactly the Bayes formula. So you can do Bayesian inverses in all Markov categories that have the right conditionals, and you can use string diagrams and twist things around here. All right. You might have heard of probability monads, and those are very closely related to Markov categories. If you don't know about monads or about probability monads, I'm going to put in the description of this video a link to a video which is an introduction to monads and probability monads. So you might want to pause this video and watch that, and then come back to here if you want. Okay. But those of you that know about probability monads, then here's the link with Markov categories. If you have a Cartesian monoidal category, so remember, no randomness, and you put a monad on it, which is first of all affine, meaning that it preserves the monoidal unit. So like probability monads, right, that preserve normalization, and which is monoidal. So you can talk about joints and marginal, so such that it has these maps that go from PA times PB to P of A times B. So you say this is like for probability monads, this is forming the product of the two probabilities as a particular joint distribution. And of course, you need these to satisfy some conditions like associativity and so on. Then if you have this, then the Kleisli category is canonically a Markov category, okay, with the copy maps induced by the Cartesian ones and so on. This is how you obtain stock, the category of Markov kernels. So Markov kernels are exactly the Kleisli morphisms for the Giri monad on MES. Same thing if you restrict to Borel stock, so what Giri was calling the Giri monad on Polish spaces. Okay, so stock and Borel stock are Kleisli categories of Giri monads on MES and the category of standard Borel spaces. Fin stock is almost the Kleisli category of the distribution monad on SAT, so the one of discrete probability. Not quite though, because you see fin stock as object has finite sets. And you see, so there's no monad of probability monad on fin set, right? Because, well, because if you take a finite set and look at the probability measures on it, then they are not a finite set. So you have to take account into that, but The Kleisli category of distribution monad on set has, again, as Kleisli morphisms, stochastic matrices, but they're like infinite, except that they're like for each column, they are 0 in most entries, like where they're non-zero, they are a finite set, and they have to sum to 1. Okay, but which set, like which support they have, might be unbounded in your infinite matrix. So that's why it's a little bit different from Finstock. But again, the Kleisli category of the distribution monad has as morphisms basically, again, a form of stochastic matrices, just slightly more complicated. Okay, and this gives us a lot of Markov categories, because pretty much every probability monad satisfies these properties, and so gives us a Markov category. All right. Now, you might know to each monad corresponds an adjunction. In particular, there's an adjunction with the Kleisli category, meaning that morphisms from A to PB are the same thing as Kleisli morphisms from A to B. That's almost the definition of a Kleisli morphism. What does it say for us? Well, this tells us that Markov kernels from A to B, or like random maps from A to B, are the same things as maps from A to probability measures on it. So Markov kernels from A to B are the same thing as measurable functions from A to PB. So they are the same as probability measures in B measurably indexed by A. Okay. Now, if you set A to be exactly PB, you see that maps from PB to itself are the same thing as kernels from PB to B. And, you know, you might expect the unit lemma coming here, and it does. So take now the identity map. That's what it means here to apply the unit lemma, in case you're not familiar. Where does the identity map go? It goes to a special map from PB to B, which satisfies the universal properties, like a universal arrow here, which you can see as like generating all the arrows here. Okay. So it goes exactly to the map that we call sample, that in some sense generates all the randomness. What do I mean? What does sample do? So it's a map that takes a probability measure, PB, and gives you a random element of B. So it takes a probability measure on your space X and draws a random sample, a random element of X, distributed according to that measure. All right? So those of you familiar with probabilistic programming might recognize the sample command, which, you know, that's what makes your thing probabilistic. That generates all the randomness. Like all random things are obtained by like sampling from some distribution, right? So for those of you that instead are more in math, in basic probability theory, you have this Bernoulli of P that takes a parameter P and gives you a random element of 0 or 1 that gives you 1 probability P and 0 probability 1 minus P, right? You might have seen this in basic probability. Now, what does this do? So P, first of all, lives in the 0-1 interval, right? But 0-1 interval is isomorphic to just the probability measures on the 0-1 two-element space. And what does Bernoulli do? You see, it draws a random element of 0-1 according to P, according to this distribution. All right. And you see, like, you can draw from, like, in a similar way, you can draw from arbitrary distributions, more complex. They are like just more complicated version of this idea, right? Yeah, random elements drawn from arbitrary distributions. Okay. And the universal property of this adjunction tells you that every Markov kernel is the composition of SAMP with something. Like it's at some point drawing from some distribution randomly. That's what makes it random. Okay. So again, the randomness can be encoded by this universal property of your category. What if you instead in this adjunction set B equal to A? So what's the other universal arrow? Well, I can leave it to you as an exercise if you want. So if you take the identity on this side, what's the map from A to PA that you get? Hint, what is the only natural construction that you can form if you take a point and obtain a particular probability measure there? Okay, try yourself. All right. Let's now go on to results that you can prove with Markov categories. The first result that I like to explain to you is the Finetti theorem. So the Finetti theorem is an old result. It was first published by Finetti in 1927. So it's old math. However, since 1927 until now, until the 2000s and 2010s, in the probability literature, there keep appearing publications that reprove Finetti's theorem, and not even in more general contexts, sometimes in the traditional contexts, but they come up with new proofs. This is telling that it's still not entirely clear what is really going on. I mean, of course, the proofs are solid, right? But people are maybe not very satisfied with the interpretation of what this really means, okay? And, you know, to make things worse, we have come up with our proof. So there's one more now, the categorical proof. But I want to argue that category theory here can really help the intuition, can really help interpreting what is really going on. Of course, if you are the kind of person for which thinking in abstract terms, thinking in category theory is helpful. And I'm definitely one of these persons, okay? So, first of all, the Finetti theorem is about exchangeable sequences of random variables, which for us can be written as a commutative diagram. So consider a joint distribution, possibly parameterized, on infinitely many copies of X, countably infinitely many. Now, I've only talked about finite products as a monoidal product. Here you can form an infinite, I want to say infinite monoidal product by means of the so-called Kolmogorov extension theorem. I don't want to enter too much the technicalities here. You can do this categorically, okay? Tobias Fritz and Eigil Rischel have done this. So imagine something like an infinitely many copies of X, possibly with correlation, okay? A distribution on there. That's a sequence, an infinite sequence of random variables. Now, this is called exchangeable if it's invariant under permuting finitely many of these components, of these coordinates, right? So imagine you have a sequence, an infinite sequence, you permute finitely many of them and just apply the identity on the rest, okay? Now, if your distribution is exchangeable, it means that this does not change the distribution, okay? So if you want, if sigma is one of such permutations, then this triangle commutes, all right? So exchangeable permutations, exchangeable sequences categorically are this commutative diagram. Now, what does Finetti tell you? Well, as category theorists, every time you see a commutative triangle, you might expect a universal one, right? You might expect a limit. And this is exactly what's going on here. So the theorem says that in Borel-Stoch and in other Markov categories that satisfy the same axioms, for every a and k, there is a natural bijection between cones over A, so commutative triangles like this, so natural bisections between exchangeable measures and arrows into Px, okay, making this diagram commute. This is a limit diagram then, it's a universal property. What does this say? There's a bijection between exchangeable sequences and random elements of Px. So there's a bijection between exchangeable sequences and probability measured on Px. That's what the Finetti theorem says. It's a limit. Given this diagram, so given this commutative triangle, there's a unique map into Px making this commute. And now, this is a limit. So what is the universal limit cone? Right? For the unit lemma, you can set A to be Px and put here the identity and so on. So what is the limiting cone? What's this universal triangle? What are these blue maps from Px to Xn? Well, the Finetti theorem tells you that too. Those are exactly these maps obtained by copying Px infinitely many times and sampling. So that's exactly taking IID samples. That's drawing a sequence of samples from the same distribution. Now, why does the copy map come in? Because you're sampling from the same distribution. It's not P and P prime. You take a distribution P, the same P, and draw random elements from P, okay? So you see, that's already enough to tell apart, PX in the limit, right? Because that's what you do in statistics. That's what you do in science. You have a distribution, and to identify it, you just sample from it many, many times. Of course, ideally, infinitely many in practice, a large enough amount, right? But infinitely many times that tells apart distributions in PX. And this is what's happening. So the Finetti theorem tells you that every exchangeable measure factors through PX uniquely in this way, through taking IID samples, okay? So I want to say already at the level of statement, category theory gives a lot of intuition about what the Finetti theorem is saying, right? It's a limit. So of course you need to have intuition for category theory. You need to have intuition about limits and limiting cones and universal properties. But once you do, then the Finetti theorem is, just one more of them. I want to say just that, but this is very deep. So as you know, universal properties look small on paper, but they can have very deep interpretations. And this is the case here too. So the Finetti theorem says that, in particular, exchangeable sequences make the copies in the sequence, the variables in the sequence, conditionally independent given PX. So you see, this diagram is exactly like, an infinite version of the pizza diagram that we saw before. So given PX, so if PX is the same, then the X are drawn independently. These are independent. Now, what does this mean? This looks a little bit abstract, like sampling independently looks a little bit conceptual. So let's come up with a practical example of what this means. Take X to be just a 2-point set, so heads and tails. So that's a coin flip, all right? Now, flip a coin repeatedly. That's exchangeable, right? Because you don't expect different results, you don't expect different probabilities on your first flip or on your 10th flip, right? The probabilities are going to be the same, right? So this is exchangeable, okay? Now, so you flip this coin repeatedly, or maybe let's say a friend of yours has this coin and flips it repeatedly, okay? And you see that the flips come out as heads, 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 heads again. Well, what do you expect to see next? Well, you might be a bit surprised that there's so many heads in a row, right? Now, your mind would be like, my friend has not shown me the coin. So maybe it's a coin with 2 heads. They're trying to trick me. So maybe I should bet that the next trial is heads. Or maybe the coin has 2 sides, but there's a little weight on one of the sides, like it's a loaded coin. And so it's more likely to get heads. And so maybe it's a better idea to, to bet heads, since I've seen so many of them, right? But what if instead your friend shows you that the coin is fair, like shows you beforehand? Then if you are sure that the coin is fair, then you don't expect necessarily heads as the next round. And you're like, okay, then these 4 heads were a coincidence. And, the coin is fair, and the coin does not remember that it came heads 4 times, right? So the next flip is going to be either heads or tails with probability 1/2. Okay, it does no memory; it's independent from the rest, right? So what's going on here? If you know the coin is fair, then the flips are independent from one another. But apparently, if you suspect the coin is not fair, it's like if you're uncertain about the coin, then it's as if looking at the sequence of heads helps you come up with the next outcome. So what's going on here? Flipping the coin repeatedly tells you something about the future? So how is it possible that if you're uncertain about the coin, then you can make a prediction based on the past? Aren't these independent flips? Where's the independence if the past can help you about the future? Maybe they're not independent. Maybe they're not independent flips. If you have uncertainty about the coin, then this history has some information about the future. If you don't know everything about the coin, there is some correlation between the past and the future. There is something in common between all these flips. What do all these flips have in common? That it is the same coin. Okay? If you are uncertain about the coin, then suddenly this randomness once again turns into correlation, as we saw before, like with the pizza example. If you don't know the coin, then it might look that there's some correlation between these flips. But once you flip, well, once you fix the coin, once you know that the coin is the same, so it's copied, then these draws are all independent. Okay, just like before, once you know where your person is from, then the espresso and the pizza are independent. Okay, once you know the coin, then these draws are independent. So you see what this diagram tells you is if you fix px, so px is like what's the distribution of the coin, right? What's the bias of the coin? Once you know px, then all these are just independent flips. Okay, so that's this diagram. And then what's the statement of De Finetti? De Finetti tells you that every exchangeable process, some of them are not trivially exchangeable, right? Are not obviously exchangeable, but all of them are going to exhibit this behavior. All of them are going to be just independent draws from the same distribution. Okay, so all of them look like throwing repeatedly from an unknown coin, or rolling repeatedly an unknown die, and so on. Okay, that's the statement of the Finetti theorem. So you see category theory. If category theory is compatible with your way of reasoning, category theory helps you a lot understanding what the Finetti theorem really says, and this interplay of correlation and conditional independence and so on. Okay, thanks to Markov categories. Markov categories also give you the proof of the Finetti theorem. You can prove it using string diagrams, but I don't want to get into that. But even, I want to say, even at the level of just a statement, I feel like a category theory already helps. But yeah, trust me, it also helps in proving it. Okay. All right, that's one theorem. I also want to present the second theorem, the deseparation criterion. So as I said before, Markov categories with these string diagrams allow you to represent graphically the structure of correlations. So in some sense, they give you a graphical model, a little bit like Bayesian networks and Markov random fields and so on. So they are one more of this formalism. All right, so if you have a joint probability measure, sometimes you want to do Bayesian inference or causal inference. So you want to say that in maybe X is the cause and Y is the consequence, or like that X is the independent random variable and Y depends on X with some additional randomness. Okay. Of course, you can condition and do the other way around, right? But let's say we want to fix X as our independent variable. So you can write a graph like this, where your observed variables are the nodes, and your correlation here, or your dependent structure, is encoded by an arrow. So you get a directed acyclic graph. In Markov category, we draw this like this. There's a triangle here, it's a state of X, and this conditional is this square. Okay. The observed random variables for us are these things, this wire appearing at the top. Okay. Now, of course, again, with conditionals, you can flip this around and so on. Markov categories give you a little bit more general things than these graphical models, because, for example, you could still have inputs here. So this could still be a kernel, and that's not encoded in these diagrams. And also there could be several different outputs here. So like joint distributions. So in particular, P of XY can be drawn as a big triangle with two output wires, and you can't do it out here. But still, for like causal inference, these graphs are still like very, very general. And I want to say the graphs are a bit simpler, right? Because you see, it's a smaller diagram than this. But let's keep going. So in this situation, you see, you want to say that, say, x depends on w, y too, and z depends on everything, but they only, so they don't have an arrow here, right? Z depends on w only through x and y, not directly, okay? How do you do this in Markov categories? Well, first of all, w gives you x and y, then x gives you z and y, but you see, you're actually also looking at w, so w is observed, so you copy w one more time. Okay, so this is the diagram. All right. Let's see, you say, okay, well, why would I want to use Markov categories here? These diagrams are so big compared to the traditional ones. Well, I want to argue that these diagrams are actually the right amount of big to make something simple, to like display in plain sight what's going on. The reason is that Markov categories can talk very easily about unobserved variables, like what's called latent variables, things that are integrated over, you know? If you didn't sum over W, then you just add another wire, just like we did here. But you see this case, which is again the pizza case of before, or like the Finetti. In graphical models, you have to add some stuff. So you have to like, there's add some special nodes, which are like kind of unobserved or crossed over, all right? To account for the correlation here. But again, here you can't really do joins, at least not in traditional Bayesian networks. So these two possible arrows here can be explained by some variable that's been like hidden, okay? But in Markov categories, this is a lot simpler, okay? So the catch to a larger diagram is that you don't have to deal with these ambiguities. And this makes the deseparation criterion easier, okay? Let me give you an example. So take this too big, so to say, diagram. Now, suppose that you want to ask, what are the correlation structures here? So, for example, here, x and y depend on w. Are they conditionally independent given w? Or does also z kind of give parts of the connection between here? So you see here, you have to look at the direction of these arrows. And so it's not just about being connected, right? They're connected through w for sure. Are they connected through z? Hard to say, right? Yeah, of course, there is the criterion, right? You have to look at directions and see if it's a sink or a source. But I want to argue in Markov categories, this is easier. So first of all, marginalize, unobserve all the things that you're not looking at here. So marginalize over z and apply your comonoid axioms and normalization axioms. You have three wires. Now, is W the only bridge between X and Y? Is it, for first of all, a bridge? Yes, you see they're connected through W. Is it the only bridge? Yes. Look, remove W, like not by marginalizing, really destroy it from the graph as a graph, graphically. Now they're separated. All right. Then they are conditionally independent given Y, because W is the only bridge between them. Topological on the graph. Really, it's a graphical thing. All right, what about Z? Are they conditionally independent given Z? Again, well, you see in this graph up to reversing the arrow, it looks very similar, right? Here though, in Markov categories, look. All right, again, marginalize, so unobserve everything you don't observe. Now remains, now W remains, but as an unobserved variable, stays in the diagram. And now, okay, remove the wire of Z, not marginalize, really remove it, like cut it from the graph. Are they still connected? Well, yes, okay. Then Z does not separate them. All right, you see, it's just topology. Now, it's just the topology of the network, but what about this? Are Z and W conditionally independent given X? You might say, no, they are also connected through Y. But again, you see, it's a little bit like before here, up to the direction of the arrows, right? It's as a diamond, as a square, it might look symmetric. But again, here, let's see what's going on in Markov categories. Again, we are unobserving y, so marginalize over it, discard it. Now, is x the only link between w and z? Well, no. See, if you remove it, there's this unobserved variable y that connects them. So no, as we thought, y remains. What about given x and y? Well, okay, now if you don't marginalize over anything, then you see removing x and y does separate them. And so, yes, okay? So it's just about the topology of the network. So it is true that the diagrams of Markov categories are bigger. However, the catch is that they are big enough to show very plainly, laid down clearly, these dependence and treat unobserved variables on equal footing in such a way that this separation, like a conditional independence, is really just about network connectedness in your wiring diagram. There's a wire from one to the other one. That's it. That's your topological connection. Okay. So it's in some sense simpler by being big enough. Okay. Maybe a way to see that is that you see you can do Bayesian networks, which are like directed acyclic graphs. But then when you want joins or unobserved variables, you want more general undirected thing, a bit like maybe like a Markov random fields instead. Okay. And so undirected things. And Markov categories are like these wiring diagrams are kind of a mixture, like the right balance of directed and undirected. Because they see it's directed as in all the things point up and all your observed variables are going to be up. But it's also undirected in the sense that you can talk about joins and unobserved variables. Like there's this horizontal direction, which is like kind of undirected. Okay. So they are two-dimensional and they have features of both directed and undirected. And because of this, the topology of the network characterizes exactly your conditional independence structure. Okay. So I don't want to argue these are better than the traditional ways. They're a bit more general, but of course there's the networks are bigger. I want to say that these things are an additional tool. You have Bayesian networks, you have Markov random fields, you also have this. So it's an additional tool in your toolbox. Really, these are useful. These are ready to be used. Use them, okay? Not to replace what's there, but to add to what's already there. This can really give you something when you analyze complex random variables. All right. Let me also spare a couple of words about how you prove this. So Markov categories are not just about graphically representing things, but they're also about proving theorems. Now, as far as I know, the deseparation criterion, so this relationship between the graph structure and the conditional independence structure, was proven in the 90s in this paper by Lauritsen. It might be older than that. This is how early I could say. But that was a finite case and the density case, like R and so on for Lebesgue. The extension to general standard Borel measurable spaces is much, much, much younger. It came 27 years later. And it was really non-trivial to prove. You see, this paper here is actually very clever, okay? So why did it take so long? Because you see, the conditional structure should be the same, right? Why should it matter if it's discrete or continuous? Well, the thing is that to get the measured theory right, it's very complex, okay? So Markov categories don't just give you graphical formalism, but this formalism does not depend on the measured theory. Like once you know you have conditions, everything just works. So Fritz and Kingler this year came up with a formalism where you can do, I want to say do magic almost, but it's very scientific and rigorous. So you look at the proof for the finite case. I mean, here I say simple, it's not simple. Like the Lauritsen did like quite some work, of course, but it's simpler in the discrete case than in the general continuous case, okay? Much simpler. So you take the simpler proof, translate it to string diagrams, and then you're done. Now, every Markov category with conditionals, so every Markov category that has those string diagrams will have that result without having to deal with measure theory. You deal with measure theory once to prove that your Markov category, like or else stock, has conditional. That's it. Then you just have the, so to say, combinatorial difficulty. Of course, their paper is very deep. They have to like come up with like 3 Markov categories to really talk about like the graph theory, so to say, of the situation. But in their paper, there's no measure theory. Okay. In the spirit of mathematics, it builds on earlier results. It can just outsource that on earlier results. And so it makes the whole formalism a lot easier. I mean, it's complicated to develop it, but once you have it, right? It's a little bit like, using integrals to calculate areas and volumes, right? Before integrals, you had to be Archimedes to come up with areas and models. Then you develop integral calculus, Newton and Leibniz and so on. Now, it's a lot easier to calculate areas and volumes because you have, so to say, higher technology, okay? And that's what Markov categories do. So they make our proofs easier in the continuous case. This is very much in the spirit of Markov category, okay? So you see, they didn't prove something new. I mean, okay, they did because the result is actually more general than the traditional one. But, and also you see, it's only 5 years newer than this one. So it could have been that they could have been the first, if history had gone a little bit differently. But even considering the known part of their statement, you see, the value here, which is very much in the spirit of Markov category, is that it gives conceptual understanding and separates it from the difficulties of dealing with the analysis part, okay? And that's, in my opinion, the biggest value so far of Markov categories. You work with the diagrams, you work with the graphs, and the measure theory just follows you. All right. This is the end. So these are the main results that we have so far. Markov categories, as we know them, are 3 years old. They came out in 19 in this paper by Friss. Of course, they build on earlier structures like GS monoidal categories and so on. But as we know them, they're 3 years old. In these 3 years, we had a lot of results of Markov categories, and researchers other than my collaborators are looking at them. For example, Bart Jacobs and Arthur Parsignat and so on. So there are a lot more results coming from us and from others. Here are some references if you want to know more, and if you want to know even more or to look at all the results of the previous slides, please look in the references of these references, okay? I'm gonna stop here. Thank you for watching. Let me just say, since this is not live, I cannot take any questions, but if you saw this video, I'm sure you know how to reach me. Please do if you want to. Thanks for watching. Bye.